we could, increase that to 60, just to, show some crazy, so now we look at, we've got, more extreme scale on this. More extreme crossover distortion, And maybe there's some useful musical application of that. You never know unless you try. A lot of stuff, especially when it comes to the topic of distortion, a lot of things, trial and error and happy coincidence and tweaking old things and coming out with new stuff. But anyway, so that's class B. Stop that. We'll look at B. So again, here I've added the extra bias. I've increased this bias and I've shifted a little more to get around the dead zone. Stop, and then bottom. Okay, so now when we operate the slider game, it behaves identical to the class A amplifier. We've gotten rid of the dead zone. You can play with the bias and adjust that. And you can do the same thing in Spice with transistors and get real, more accurate models of these. But this is just kind of a notional thing, so it's abstracted out the device itself. Okay. All right. So the last one is the class D, of course, the most interesting. And the class D was actually the one I did first, because it was, I read an article in IEEE Spectrum on class D amps, and they had some notional block diagram within the schematics. You look at the schematics, you don't make heads or tails of that. You can follow it through, but it doesn't illustrate the point as clearly as a good block diagram in this case. Whereas I think with the class A, B, AB, it may be harder to understand the abstract ones because we're so used to looking at amplified schematics. So with this one, the abstract notion, all right, so we're going to start it up. So this is the input signal. That's our sine wave. Then here is our pulse width, and the nice thing is to get it right. So we can line it up. You can see, the high points on this one correspond to the wide pulse widths. Let's see if there's I think if I stop it, it actually pauses. Oh, there's pause. That's it. Okay, so there you go. So, there's a little bit of offset because of the way the figures are, but you can see that this input corresponds to the wide pulse width, and this low corresponds to the very narrow pulse width. Actually, sorry. Okay, what? The time scale is off too. That's really different. So, trust me, it lines up. You can play with these how you really want to see it, but it does line up. And then the beautiful thing is, you can hook up this one, and you look at it, and you say, looks good. You pretty much got the input signal back.
Wow.
And then what you can do is, you can actually go in here if you want to see, how to. Yeah, it's a pretty high order, by the way. So, but we can reduce that to that. Can't do that long. Well, that makes sense. That's asking a bit much.
Yeah. Pull that, pull that from right.
Yeah.
Yeah, look at
So
that.
there you go. Now you got a lot more noise coming through because, yeah, seventh order is going to give you, yeah, what is it? It's 20 dB per decade per pole.
I just did the, JLab and fifth order drop it. Or no, wait, not fifth order. Yeah, yeah.
Yeah, well, that's all the way to like the last one. Right?
So I think because the first order gives you 2 poles in the complex, right? So
Yeah.
seventh order actually gives you 14 poles. So, you remember how to make a Butterworth filter? All the poles are on a circle. That was something I forgot after school, but I looked back up. That's how you make a maximally flat, or maximally flat is what a Butterworth characteristic is. And so like that, I forget that that's called the second order or fourth order. The polynomial is actually fourth order.
Yeah.
Yeah, that's right. That's a fourth order. So fifth order would actually have the 1, 0. It would have one real pole, and the rest would be
Yeah.
yeah. So all right. So a seventh order has 7 poles. That's right. So by having everything here, you're lining them up so that it gives you the maximum transmission. So yeah, that's it with a low order, and then as you increase it. So that's again part of the difference between something that may have a very good output filter and something that may run it straight into a speaker. A speaker is going to be a first order, but if these are all super hearing, way above 20 kilohertz, then it may not matter. Or the speaker won't reproduce them. So, you get into an interesting case where you can model a speaker with a low-pass filter, but then it's really extreme at the upper end. It's not a linear low-pass filter, right? Because there are things that you can't reproduce. Okay, why don't we take a break? We'll come back and we'll do the tube introduction.
Yeah, just think about the speaker with low pass. It's kind of interesting because it's got like a physical component about it that just can't, it won't vibrate.
Yeah. Yeah, and strictly speaking, it's also it's a bandpass really, because speakers can't operate below a certain point.
Right.
They make a certain